Interpreting IR scans for experiment 8, double dehydrohalogenation of dibromostilbene to diphenylethyne. We're forming an alkyne. So here is a Vic dihalide, 2 molecules of KOH at very high temperature, about 200 degrees C. Remove 2 molecules of HBr from adjacent carbons, producing 2 pi bonds and forming an alkyne, in this case diphenylethyne. Quickly to review, in general you must make assignments for the major absorption bands of the pure reagent, pure product, and recovered product. And you can look at the structure of the molecule first to identify the types of functional groups. Look at the generic scan in the notes for the functional groups present. Then go to the assignments table and make the appropriate assignments, and then put those on your scan. Step 1. Dibromostilbene, the reagent, has already been studied in experiment 4, so I won't repeat that here. We're going to only interpret diphenylethyne, the product. So our product, diphenylethyne, you can see contains monosubstituted aromatic rings and an internal alkyne, and that's all. And since the infrared absorptions of aromatics have already been discussed in the IR video part 3 for experiment 4, I won't go over those again here. We'll simply focus on the internal alkyne. So step 2, we want to look at a generic scan of an alkyne. You'll find this on page 105. Now the generic scan is for a terminal alkyne, in this case 1-hexyne, and we have an internal alkyne. The CH stretches and bends for a terminal alkyne are shown here, but again they won't apply to our internal alkyne, so the only evidence we have is the carbon-to-carbon stretch. In the case of a internal alkyne, this occurs at about 2220 wave numbers, just a little higher than it would in the case of the terminal alkyne. Step 3 is we're going to look at the assignments table for alkynes, and that's on page 118. And again, the only thing that applies to us is the carbon-to-carbon stretch of an internal alkyne at about 2220. Unfortunately, this is very small or perhaps completely absent when the symmetry of the molecule is high. This molecule is completely symmetrical around this center line, like mirror images. And so we see little, if any, absorption in that range. Little evidence, if any, for an internal alkyne. Step number 4, I'm going to have you make assignments for the absorption bands in our product diphenylethyne. So to begin with, let's look for evidence of the carbon-to-carbon triple bond stretch at 2220 wave numbers, right about here. And you see there really isn't much there. In all honesty, if we weren't looking for a specific band here, we would not identify this as anything other than baseline noise. All we can say is there should be an absorption band there in alkynes that are not so symmetrical. All of the other absorption bands that we see here are clear evidence of the monosubstituted aromatic ring. So you will only have 2 IR scans to interpret for this lab, the pure product diphenylethyne and your recovered product. And this is because you've already submitted an IR scan for the reagent dibromostilbene. So look for evidence of the residual reagent dibromostilbene in the IR scan of your recovered product, alkyne. And that's it. I hope that helps.